There we go. Yes. Okay. Hello. Thank you for coming to the third seminar in the 2022 Science in the News Public Seminar Series. So tonight, our speaker is Andrea Salazar, a PhD candidate in the Department of Earth and Planetary Sciences. And today, she will tell us about the hunt for Earth 2.0. What makes a planet good for life?
Thanks, guys. Thank you all for being here. So we've heard a lot in the news pretty much all the time about, we're looking for a planet that is really similar to Earth because we're trying to find life somewhere in the galaxy. And in this talk, I'm going to kind of challenge this idea that a planet needs to be exactly like Earth in order to be considered habitable. So on Earth, we have these brilliant scientists that I like to refer to as the alien hunters. And they're brilliant. From Earth, from telescopes, we've found over 5,000 planets already. And this is likely just a small fraction of the planets that are out there waiting to be discovered. But there's this other sector of people who are interested in exoplanets that I think don't get as much attention. And those are called, or what I call them, is alien real estate agents. And this is the genre that I kind of classify myself in. So based off of the information that these alien hunters find for us through telescopes, I run simulations on my computer to try to figure out what kind of planet an alien would like to live on. So we can put this sold sign on one of these planets, and then we'll know that a planet like this could be good for life. And so I'm going to treat this seminar kind of like your induction into this real estate agency for alien hunters. And we're going to break the talk into 3 different sections. Each section will be about 20 minutes, and we'll have questions after each section and a little bit of a break so you can gather your thoughts. The first part is going to focus on our pale blue dot, which is what Carl Sagan famously called the planet Earth. And you should be very familiar with this planet. In part 2, we're going to talk about feedbacks that make or break habitability on planets that are like Earth but also different from Earth. And we're going to end with what is probably the most fun part of this talk, is exploring if planets that are very different from Earth could be habitable. So this is part 1, our pale blue dot. And spoiler, our pale blue dot was not always as peaceful as it seems today. So I'm just going to start with this beautiful image that NASA has. This is a real image of Earth. And I kind of want to solicit from you guys some things that you know about Earth that you think makes Earth a really good place for us to live. That makes Earth a good habitable planet.
Water.
Water, good, yes.
Atmosphere.
Temperature.
The ozone layer that shields us from the radiation from the sun.
Yeah, ozone, definitely. I heard a lot of good ones. Atmosphere, we got clouds, we have continents, we're the right distance from the sun. There's a lot of things about Earth that make it seem really special. And there are a lot of people who believe that it's very unlikely that we would have a planet that has all of these perfect elements together. And so in my work, when I'm thinking about other planets, I really have to consider if we need all of these things, or if we need any of them, in order for a planet to be considered good for life. And that's a big question mark. I think that, depending on who you talk to, you're going to get a different answer. So before we really launch in, I'm going to start with some brief definitions for people who aren't super familiar with this field. When I say atmosphere, what I'm talking about is the gas envelope that surrounds the solid part of a planet. So this is a picture of Earth's atmosphere. You can see it's pretty thin, but it actually makes a big difference. So this is the gas surrounding the planet. And I'm also going to talk a lot about greenhouse gases. And we don't have to get too scientific in exactly what a greenhouse gas is, but I'm going to make an analogy with a greenhouse gas being like a blanket. So a really strong greenhouse gas is like a really thick wool blanket. It really insulates you and keeps heat in, and it warms you up. Versus a weaker greenhouse gas is kind of like those really flimsy airplane blankets that they give you that, provide a little bit of heat, but it's nothing to write home about. And so I'll talk about the thickness of the blanket when I'm talking about greenhouse gases. So we're going to start with testing what you know about habitability. I'm going to show you a few planets, and we're going to decide together, just call out yes or no, if you think this planet could potentially have life on it. And some things to keep in mind is you have to think about if it's too hot or too cold for life, because life likes it at a very specific temperature. You should consider if we can breathe on a planet like this. And also, a big one is there water, liquid water specifically. Okay, we're going to start with a tricky one. This is a planet that has clouds, but the clouds are made of sulfur. And it has an atmosphere, which is good, but the atmosphere is about 90 times as thick as Earth's. And the real killer on this is that the surface is 700 degrees Fahrenheit. And a fun fact about this planet is that it rotates very slowly, but also backwards. It kind of looks like it's spinning upside down. What do you guys think, this planet?
No.
Seeing lots of no's, and you're right, this is Venus. And if you know anything about Venus, yeah.
Oh, can I ask a question?
Sure.
Wait, what is
That's a really good question. So we're going to save questions till the end, but I'll answer this one. So what I mean is that Earth spins the same direction that it orbits. So it's like counterclockwise. It rotates and orbits the same way. But Venus rotates clockwise instead of counterclockwise. So it's like rotating and orbiting in a different direction, which is weird for planets in the same solar system. Okay, this is our next planet. This planet also has an atmosphere, but it's really thin. This atmosphere is only 1/100th as thick as Earth's. And the surface is really cold. It's about minus 80 degrees Fahrenheit on average. It has 2 moons, which is kind of cool. And there is ice on this planet, but it's trapped in a solid form at the poles. Though it's possible that there was water earlier in this planet's history. Yes? No?
No.
Yeah, good. Okay, yeah, this is Mars. Probably not, but I think that, we're very interested in looking at this planet closer to see if maybe there are fossils from previous life that could have been on this planet. But it's open to questions. Okay, these were easy. These are planets that you know very well. We're going to move to harder planets. So this planet is only gets about 3/4 as much sunlight as modern Earth, so its sun isn't as bright. We think that there's probably a global ocean underneath all of this haze, but it's covered in this really thick methane-like atmosphere. And there's no oxygen on this planet. What do you think? Some no's, some maybes, some questions? You should be confused. This is Earth, 4 billion years ago. And what's interesting about Earth at this time is there was life on Earth. In this time when it looked really different from today. There wasn't even oxygen on this planet, but this is when life was beginning on Earth. And we'll do one more. This is a planet that's completely covered in ice. It has oxygen though, which is good, but the equator is as cold as Antarctica. So the hottest part of the planet is as cold as Antarctica. Completely frozen.
Yes.
Some people say yes. Yeah, because we got some good water. Okay, good. This is also Earth. You guys are catching on. This is Earth about 2 billion years ago. And not only is there life on this planet, there's pretty complex life doing photosynthesis on this planet. So what I'm hoping that you've kind of seen is that Earth throughout its history has looked really different than it does today. And so I think that having this idea that a planet needs to be exactly like modern Earth is flawed to begin with, because we know Earth had life on it a really long time ago, back when it looked completely different. And so to kind of hammer this point home, I'm going to give you a brief tour of the history of Earth. We're going to start 4.5 billion years ago when Earth formed, and we're going to move forward in time. And we're going to start right when the sun formed. So the sun formed from this dust of gas, and after it formed, it still had this dust of gas around it called the protoplanetary disk. And it's from this disk that all the dust grains are going to kind of collect together, and you're going to start forming tiny little planets, or things that will grow into planets. So this is a tiny little baby Earth, and as it starts orbiting around the star, it collects all of the material that's in its immediate neighborhood. And so you can see it's kind of carving out this disk in the protoplanetary disk, and it's getting bigger as it does so. So this is Earth very soon after it formed. And yeah. Okay, so now we have our little baby Earth. It's completely covered in lava. It's like melted rock, because the collisions that formed this planet made it so hot, there's so much energy in it, that it's just completely like a lava planet. And things just don't get any better for Earth. We have this Mars-sized object that we're pretty sure smashed into Earth, and it blew it to smithereens. And from the dust and fire and catastrophe of this, we formed what is now the moon. And so the moon is actually made of the same stuff that the Earth is made out of. And this is our, as scientists, explanation of how this happened. And so now we have what will be the moon that we know and love, but Earth is still pretty much a molten lava planet. And obviously no life can exist. Well, life that we know of at least can't exist on a planet that is completely melted and covered in lava. And you're thinking at this point, like, things have to get better for Earth. But no, that's not true. So after that, we're hit with this event called the Late Heavy Bombardment, which is where all of these asteroids from further out in the solar system get, like, sent into the inner solar system. And that's how we formed our craters on the moon. And after this is over, Earth finally has enough rest to cool. And as it cools, it forms a rocky, solid surface. So now we could walk on this planet finally. And from the lava, gas comes out. And this gas is what is eventually going to form our first atmosphere. And so this is finally looking like a more recognizable version of Earth. But we'll see that it's still nothing like the Earth that we know today. So what was going on? This is now, let's say, 4 billion years ago. This is pretty much what we think was going on Earth. So we're pretty sure we had a good amount of water. Whether or not there were continents, that's pretty unclear. The rock records just don't go back that far. We're also pretty sure that the atmosphere was pretty thick and it had a lot of methane in it. Methane is the stuff that like cows fart, and so this wouldn't be a very good smelling planet. But another interesting fact about Earth at this time is that the sun was much dimmer than it was today. It was about 75% as bright because stars get brighter as they get older. And so even though this planet doesn't look very much like Earth, we do know that life was forming during this time. And we think that life was forming down deep in the ocean near these vents in the ocean that spurred out really hot, like nutrient-rich gases. And so we have our little organism, little single-cell organism, eating that up, and they think it's very delicious. But at some point, a little bit later, these organisms start to think, man, that sunlight looks really, really good. And so they start migrating up to the top of the ocean, and this is when photosynthesis begins. And what we've all learned about photosynthesis in our high school science classes is that these organisms take in sunlight and they breathe in CO2, which is carbon dioxide, and then they breathe out oxygen, like oxygen in the form of gas. And so because these organisms are now breathing out all of this oxygen, we finally have oxygen in the ocean. Well, we have oxygen that's separate from like H2O. It's not locked up in anything, it's free to kind of roam around. And over time, through mixing with the atmosphere, that oxygen goes into the atmosphere. And now we finally have an atmosphere that has oxygen in it, which is good for mammals like us that need oxygen to breathe. Things should be good now, but it's not good. Things are about to go really bad. So I'm going to do a little bit of chemistry, but we're going to keep it pretty simple. So methane is a very powerful greenhouse gas. It's like the thickest wool blanket. It's really good. But the problem is when methane combines with oxygen gas, which is now in the atmosphere because of photosynthesis, it makes carbon dioxide. And though we all know from talks of modern climate change that carbon dioxide is a greenhouse gas, it's not as powerful as methane. And so what we're doing is we're pretty much swapping out this really thick wool blanket for a much thinner one, but we're not giving the planet any more heat. And the planet freezes pretty rapidly after that. So this is what we call snowball Earth. This happened a little bit after the beginning of photosynthesis. And we're pretty sure that this was caused because of all this new oxygen that was in the atmosphere. And what's amazing about an event like this is it didn't kill off all of the life on Earth. I mean, it killed off, don't get me wrong, it killed off a lot of life on Earth. But in a way, it kind of forced life to become smarter and more complex and to be able to withstand really big, like cataclysmic events like this. Eventually, we were able to escape the snowball Earth phase, and things still did not get better. This is, pretty close to modern day, and we have this 6-mile diameter asteroid that plummets into the Earth around the Gulf of Mexico, and it makes the dinosaurs go extinct. So that's not good for the dinosaurs, but it ends up being good for us. But what's interesting about this, and I think it's kind of a misconception that people don't know very much about, is that it wasn't the asteroid itself that killed the dinosaurs. What really killed the dinosaurs is when the asteroid smashed into Earth, it blew up all of this debris into the atmosphere, like this really thick dust that just doesn't allow any sunlight to get into the planet. And this completely wrecked the food chain because the plants couldn't do photosynthesis, they all started dying, and then up through the food chain it went, and then all the dinosaurs unfortunately went extinct. And the latest climate disaster, minus modern climate change of course, that happened over the last 2 million years or so, is that we've been going through these cycles in our climate where we go between times when we had a lot of ice cover and it was very cold, and then we had less ice cover. And these oscillations are happening every 50 to 100,000 years. And this is pretty rapid on like a planet timescale. And you would think that life wouldn't be able to withstand these huge changes in temperature. But actually there are humans, or at least our descendants, on the planet at this time, and we were able to make it through. And so what I want you to take away from this specific section is that life is really resilient, and I think that life's history on Earth shows that really well. And also that Earth is not a perfect planet. I think that it has survived many disasters, it's survived many more than the ones that I've put up. And I think there's no reason to believe that a planet has to be perfect in order to survive long term, or to allow life to survive long term. And also the things that make Earth really good for life that we kind of talked about in the beginning, that wasn't always true. And so I think that when we're looking for other planets, we should be more careful in the criteria. criteria, and that's what we'll go into in the next few sections. So is there any questions about this specific section?
Great. So yeah, we can take questions from the audience here live, and then if anybody's watching on the YouTube live stream, feel free to type any questions that you have into the chat, and we'll give them to our speaker. So yeah, if you have any questions?
So you mentioned that the Earth, formed its moon as a result of kind of a collision at some point early in its evolution. Is that how most moons within our solar system are formed? Is it a pretty common occurrence that moons are just the byproduct of the original planet?
That's a really good question. So in our inner solar system, where we have like Mercury, Venus, Earth, Mars, the Earth is really the only one that has such a big moon, and we think in order to get a really big moon like that, like the moon is only a tenth the size of Earth's, which is pretty big, you would need a collision, because the Earth's gravity just wouldn't be strong enough to like catch an object. But for most, I think like for the moons of Jupiter and Saturn, those were formed from like the debris field that surrounded the planets when they first formed, and could be from collisions too. But I think that the Earth-Moon system is special, and we're not sure how likely it is that that could happen to another planet.
So, somewhere I remember to listen about some of the components that we have right now in the Earth, like a gold. It was something was originally here in the planet, but it came in asteroids, and they just got impact the Earth, and that is why it's called we have gold right now. So, can we assume that some big percentage of the Earth is just actually not just like all the time the sphere that was just looking around, but is a lot of the mass of the Earth is from other asteroids coming and crashing the Earth? And how much do you think should be the percentage that was originally the Earth versus how much is increased from these asteroids? Because a lot of the components of the periodic table that we have right now are not original from the Earth, but is coming from another different places.
Right. Yeah, I think that's another great question. I think this is still an open question. I don't know specifically about like some of the heavier elements, but I do know for our water content, we think that a lot of it came from asteroids coming to Earth, and not necessarily from the original stuff that Earth was made out of. I think when it comes to like the original atmosphere the Earth had after it cooled down and outgassed, I think that the atmosphere you end up with has a lot to do with what the magma is made out of. But what the magma is made out of has a lot to do with the stuff that formed, which comes with asteroids and just the dust that was around at the time. But yeah, I think that's a really great question. I think it's an open one for sure.
Do we have any other questions? I had a question.
Sure.
I was wondering how they know that there was life, there were some organisms like at the bottom of the ocean 4.5 billion years ago.
That's a really good question. I don't want to say the wrong thing because I'm definitely not an expert there. But I do think that we have fossils. And I think they get buried in the deep ocean, like under stuff that protects them, and we just dig them up and see them. But I'm not 100% sure on that. But that is how we find a lot of fossils.
Awesome. So again, if you're on the live stream on the YouTube, you can type your questions into the chat. And at this point, we'll take a couple-minute break, and then we'll come back at about 6:57 for the second part.
Strap in, just 2 more parts.
All right, 6:57, so we can go ahead and get started with the second part.
Okay, great. All right, part 2, we're getting into the nitty-gritty. Now we're going to talk about different feedbacks that exist on different types of planets that can make or break whether or not it could be habitable. And pretty much this section is going to talk about how planets can go horribly, horribly wrong, which I think is fun. Okay, so the good news is that we have really great examples of pretty much everything we're going to talk about in our very own solar system. So we have Venus, which is similar to Earth in a lot of ways, same size, but it's really dry. It's super hot. We talked about how it was 700 degrees Fahrenheit on the surface, and it has this really thick atmosphere, like 100 times thicker than Earth's. And on the flip side, we have Mars, which is a little bit smaller than Earth, and it's really dry, even though we think maybe there was water on it previously. It's super cold. The atmosphere is so thin, I mean, no amount of terraforming, I could make this atmosphere like Earth. And then in the middle, we have our beautiful oasis that is Earth, with liquid water, the right temperature, pretty stable climate, despite everything that I just showed you. And I really want to ask this question of what happened to Venus and Mars that made them as terrible and unlivable as they are. So I'm going to introduce you to the number one most important rule in alien real estate. It's all about location, location, location. Thank you for the page title. I'm going to introduce this concept called the habitable zone, which some of you may have heard before. The habitable zone is the range of distances from a star in which a planet could feasibly have liquid water on its surface. So liquid water is really the key to a lot of our ideas about habitability. If you're too close to the star, then all that water is just going to boil off. And if you're too far, then the water is going to freeze, and life can't use frozen water, at least not any life that we know of. You have to be somewhere in the middle, just right. Sometimes we call it the Goldilocks zone, if you know the story of Goldilocks and the Three Bears. Not too hot, not too cold, just right. So we're going to start on the hot side. If a planet is a little bit too close to its star, what terrible things can happen? And so in the title of this section, I talked about feedbacks. That's kind of a jargony thing to say, so I'm going to explain a little bit what I mean by a feedback. There are two different types. There's a positive feedback and a negative feedback. A positive feedback is when different forces at play in the system turns a really small push into a really big push. So a really good example is if you had a bowling ball on the top of a hill, and you give it a tiny little push, gravity is going to pull that bowling ball all the way down. So this tiny push that you give it turns into a big push, just because there's some forces at work here. And a negative feedback is the opposite. It's where you give it a tiny push, but different forces in the system just return it to where it was before. So if you had a bowling ball in a bowl, and you push it up a little bit, it's going to try to go far away, but gravity is just not going to let it, and it's going to come back to where it started. And these are these two ideas is kind of what makes things go bad for planets. So when you're a little bit too close to the star, you're getting a lot of heat from the sun. And the way that a planet stays the same temperature is it gets energy from the sun, and it has to release energy somehow, and it releases heat off of the surface. That's what those red lines are. And so when everything is balanced, the heat coming in versus the heat coming out, you get a nice stable temperature. But let's say for some reason or another, the star gets a little older, it gets a little brighter, you get more heat from the sun. The temperature is going to increase a little bit, which is going to cause some of the ocean to evaporate. And that's going to put water molecules, H2O, into the atmosphere. And the thing about H2O is that if you thought methane was a good blanket, H2O is the best blanket there is. It's going to trap a lot of heat coming from the surface, which means that the Earth is trying to dump all of this extra heat that it has, but it's having a hard time because the water is blocking it. This is going to lead to an even bigger increase in temperature, which will evaporate more ocean, which puts more water into the atmosphere. That's going to trap more heat, the Earth is going to get hotter, and the cycle will pretty much just go on and on until the planet completely runs out of water and it's, unlivable. We think this is an idea for what happened to Venus. And so this is an example of a positive feedback. You give it a small push, which is a small increase in temperature from, let's say, the star getting brighter. This leads to more evaporation of water into the atmosphere. And since water absorbs heat really well, it's going to trap the heat. Less heat can escape into space. And this is going to increase the surface temperature again. And we're just going to go around and around in this loop. And pretty much the only thing that can stop it is you running out of water. And this is bad. This means that a planet is very unstable to losing all of its water. And that's not good for us. So small push turns into a big push. Okay, but what about on the flip side? What about the Mars-like planets that are a bit too far away? So let's say we had a planet that had a little bit of ice, kind of like Earth, and it has some sunlight coming in. The thing about ice, and for those of you who go skiing, for example, you know that snow and ice are really reflective. One time I went skiing and I got a sunburn on my chin because the snow was so reflective. Which means that when the sunlight hits the ice, it's going to reflect some of that light into space. So that light can't get absorbed by the surface. So if there's a little bit of ice, that's not too big of a problem. Like Earth has a little bit of ice and it's not too bad. But if you increase how much ice there is just a little bit, the planet's going to reflect more sunlight, which will decrease the temperature of the planet, which will grow more ice, because a colder planet should have more ice, which will reflect even more sunlight. And you're just going to get colder and colder and reflect more and more sunlight until finally the planet is just completely covered in ice. And it's too cold, and there's no liquid water. So this is the freeze out. This is the opposite of the runaway greenhouse. And this is not good. This is a positive feedback, right? Because you have a decrease in surface temperature, that's your small push. And because it's colder, you form more ice. And since ice reflects a lot of sunlight, you're going to get less sunlight absorbed at the surface. So the planet's going to get colder, which is more ice, more reflection, less sunlight at the surface, and colder, on and on, until you're completely covered in ice. And so what I've just shown you kind of paints a very pessimistic idea of what's going to happen to these planets that are kind of on the border. And you think like a planet would have to be like the perfect distance from the star in order to avoid these feedbacks. And I thought that too when I first learned about these. But the good news is we have a saving grace, and that's the carbon cycle. And the carbon cycle is a negative feedback, as I'll demonstrate, which helps to mitigate these like runaway effects from happening. So the way that CO2 moves through the Earth and the climate, and the atmosphere, is you get a bunch of CO2 being released by the volcanoes through eruptions. And in the atmosphere, the CO2 kind of dissolves in the water. And when it rains, all that rain goes into the ocean, that takes CO2 out of the atmosphere, and then eventually makes its way back into the inner Earth, where it gets released again through the volcanoes. And something you need, the only physics thing you need to know here is that when it gets warmer, it's going to rain more. And that's just because it gets more humid and more rain is going to form. So let's say we have a planet that's a pretty medium temperature. We're going to say we're not going to change how much CO2 is coming out of the volcanoes. Pretend that's constant. Let's say we increase the temperature a little bit on the planet. This is going to make it warmer, which means it's going to rain more. So more CO2 is going to get taken out of the atmosphere. And because CO2 is like a blanket, if we take CO2 out of the atmosphere, we're creating a thinner blanket. So that means Earth can release heat much better. And that's going to decrease the temperature again. So you can see that there are these processes in the climate system that kind of backtrack from these small changes in the temperature. And this will return us to the initial temperature. And this, thankfully, is a negative feedback. You have a small push from the increase in surface temperature, and because it's warmer, it's going to rain more. That'll mean there's less CO2 in the atmosphere because it all got rained away. This is a thinner blanket, and so that'll decrease the surface temperature. So we've escaped this dreaded positive feedback loop. So let's return to the alien hunters. Those feedbacks are things that we've kind of, found out just from studying Earth. But it's really these alien hunters that are getting all the data that we really want. So they look in their telescopes and they find out everything they can about these planets, which honestly isn't much, but it's impressive that we can find them at all. They can tell me things like how far the planet is from the star, which we know is important. Maybe the size of the planet, the mass. We can estimate if it's made out of rocks like Earth or if it's made out of mostly gas like Jupiter. And we can maybe, but not really, we're getting there, guess if there's an atmosphere. And someday, we're hoping to figure out what's in the atmosphere, because we're going to find out that what's in the atmosphere is actually the most important part. So they type up all of this, and they put it in papers and journals, and then alien real estate agents, that's me, on my computer. Everything I do is on my computer, with my trusty coffee by my side. I use math and equations and computers to figure out how the temperature on these planets would change over time. And if the temperature is the right temperature for liquid water, then I can say maybe this planet is habitable. But it's harder to do than the way that I've made it look. How can we tell if a planet is going to be the right temperature? It isn't enough to know how far the planet is from the star. Because there's a lot of variations in the temperature of a planet based off of what it's made out of or what its surface looks like. So for example, we could have a planet that's a good distance from the star that looks just like Earth, has a really good temperature. This is a habitable planet. But something we don't know is maybe it's covered in ice. And if it's covered in ice, it's going to reflect a lot of that sunlight, and it's going to be really cold. Or, on the flip side, maybe it's the same distance from the star, but it has a really thick atmosphere that has a lot of greenhouse gases in it. This planet's going to be way too hot for life to be on it. And the way that the science is right now, we have no way to tell the difference between these three things because we don't have enough information. And we're hoping the future telescopes that are better at looking at these planets will be able to tell us. So from this section, you should take away that the way that we've defined habitability in our field is the most basic definition. It has to have liquid water on the surface. And one of the most important things for whether or not it can have liquid water is how far it is from the star, because the star is the main source of heat on these planets. But the details of the atmosphere and the surface are very important to figuring out, exactly what this temperature is. And in the next section, we're going to go into specifically why the atmosphere is so important. And we're going to look at planets that are very different from Earth.
Great. If we have any questions from the audience, and then again, just a reminder, if you're watching on the live stream, you can type your questions into the chat, and we'll get to those.
So I guess I'm curious what sort of information would be like the future telescopes, what is the interesting information? Is that like sort of spectroscopic information? I guess like has any of the like transit spectroscopy been useful, or are you making like direct imaging spectroscopy?
That's a great question. So what I'm most interested in, for me personally, I want to know what is in the atmosphere, but also how much of it, right? Because we can detect, like JWST's detected CO2, but it's very difficult to tell how much CO2 is in the atmosphere. I'm also very interested, well, I think we'll get into it more in the next section, of like how quickly the planet is rotating. And I think that thermal phase curves could really help with something like that. But for direct imaging, I just am not sure, I mean, you would know better than me about direct imaging, but whether Earth-sized planets in the habitable zone, I don't know how close we are to direct imaging them. So I think that transit spectroscopy is a good place to start. 2050. I'm just gearing up for that.
Also, I didn't think we were talking about scarcity plus.
Yeah. I would just love to know what's in the atmosphere. That's my first goal. And if there's water vapor, I'd love to hear that too.
Yeah, the people that constraining abundances using the Roman space telescope. So Roman won't be able to give you Earth-sized planets, but it'll be able to constrain certain elemental abundances from spectroscopic information.
In hot Jupiters.
I don't know hot Jupiters, because that's really close to the sun.
Right.
Like sort of further out of Jupiters.
Cool. Sophia, thankfully, is going to build the telescope that does this for me, so I'm lucky.
Do we have any other questions?
So spectrography is when you can review, you can look into the electromagnetic waves, and based on the longitude and valleys and that kind of things, and the colors, and then you assume where it's coming from, that electromagnetic, right?
Mm-hmm. Yeah, so the specific example that we were talking about with transit spectroscopy, one of the number one way we find exoplanets is we look to see the planet pass in front of the star, and there will be a tiny dip in the brightness of the star when the planet crosses in front because it's blocking a little bit of it. But if you had an atmosphere, say, made of CO2 that absorbs a lot of radiation, the planet's going to look a little bit bigger than it would if it didn't have CO2 on it. And so based off of how much bigger it looks, we can kind of estimate, number one, if there's something like CO2 on it, but also how much CO2. But I think it's a very new science and it's very exciting, but I think the science has a lot of ways to go.
I was just wondering, like, kind of on the same note. So, if you're looking at spectroscopy versus like transit spectroscopy, right? So, like, how, if you have like the data of like a planet going in front of the sun, right, and like the intensity of light you get like decreases, how can you tell the difference between a smaller planet and a bigger planet that both have like no atmosphere versus a smaller planet that has an atmosphere? Does that make sense?
Yeah, that makes sense. So yeah, I didn't explain it super clearly. So we don't just look at the same wavelength of light, because different gases absorb at different wavelengths. So what they do with transit spectroscopy is they look at the star in like a range of wavelengths of light, and they're going to see that there's a certain wavelength where it looks a little bigger. And if we know that like CO2 absorbs in that wavelength, then we'll be like, okay, that's probably CO2.
Okay.
Yeah, so we have to do, the spectroscopy part is looking at multiple wavelengths of the light. So that way you can tell that it's not just a bigger planet.
Great. Any last questions? All right, it's 7:12 now, so we'll get started with the third part in 3 minutes at 7:15. It is 7:16, so we go ahead and get started with the final part.
Okay, this is the best part, I think. So I hope you guys are as amped up as I am. We're gonna look at some planets that are completely, like not even slightly like Earth. And I want you to suspend your disbelief and stay with me that I think planets like this could be habitable. And I think we just need to be a little bit more open-minded. Is it a deal breaker if a planet's not like Earth? And I love a good underdog story, so I root for these planets that are very different from Earth. So all real estate agents will tell you that sometimes your client is a little bit too picky, and so we're doing these searches for planets just like Earth. There are zero matches. We're never going to find a planet that is exactly like Earth. Earth is special in its own right, but all planets are special. Nothing is ever going to be just like Earth. And so sometimes you kind of have to push the client to expand their idea of what could be a good home. So we're going to talk about 4 different homes. The first is going to be the home that has some unnatural lighting. These are tidally locked planets. I'll explain what those are. We're also going to do the planet with the wonky floorboards. These are planets that are very tilted. And then there are planets that have a really long commute. These are rogue planets that don't have a star at all. They're just floating out in the dark all by themselves. And last, I'll propose a condo. I'm going to propose moons instead of planets. We're going to start with tidally locked planets. These are my favorite planets. These are the planets that I studied in undergrad and I'm still really interested in studying now. We have a really good example of what tidal locking is right here in our neighborhood. The moon is tidally locked to Earth. And what that means is that the same side of the moon is always facing the Earth, and the other side never sees the Earth. This happens because the Earth's gravity is really strong, and over time it just kind of causes the planet to slow down its orbit so that it becomes tidally locked. There's a lot of physics that goes into it, but I'll ask you to just believe me that this happens. And the most important part of this is the same side of the moon is always facing the Earth, and the other side never sees the Earth. And this happens because the moon is very close to the Earth. And so when I introduced the concept of the habitable zone, I really only talked about the habitable zone around a star like ours, but our star is not really a very special star. I mean, most of the stars in our galaxy don't look like our star. About 75% of the stars in our galaxy are these really small, dim red stars. We call them M stars. And so because they're so small and so dim, their habitable zone has to be very close to the star, because the star's not very hot, so you have to be really close to it in order to have liquid water. And this kind of starts to look like an Earth-Moon system, with like a planet very close to the star, kind of looks like a moon very close to a planet. And this causes planets to become tidally locked to the star. And what this looks like is that the same side of the planet is always facing the star. It's receiving sunlight 100% of the time. And this side of the planet never sees the sun, so it's really dark. You can imagine that a planet like this would have really crazy temperature differences between one side and another. So like the left side would be really hot, the right side would be super cold, it doesn't get any sunlight. And this seems hopeless, right? For example, this is an artist's impression of what a tidally locked planet would look like. Assuming it had water, the day side, which is the side that always sees the sun, is gonna be really hot. I'm actually shocked they put water on it at all. I would think it would boil off. Whereas the other side is completely covered in in ice, because it's so cold over there. It can get so cold over there that the atmosphere will just collapse. It's just too cold for the atmosphere to exist. I've painted a pretty bleak picture of tidally locked planets. You might be asking, Andrea, why are these your favorite planets? And it's because I think they're an underdog. And we think that most habitable zone planets are gonna be tidally locked because most stars are M dwarfs. This seems hopeless. But another fundamental law of physics that I'll ask you to believe me on is that hot things move towards cold things. And so if this planet had an atmosphere, the atmosphere would try to move the really hot air towards the cold side. And if you had a thick enough atmosphere, then it could kind of smooth out these temperature differences between the day side and the night side. So the atmosphere could kind of like make the hot part a little bit less hot and the cold part a little bit less cold, so it's more uniform. And people like me have done simulations on our computers that kind of show that this could happen. So if it had an atmosphere, it might not be too bad. And this is going to be a theme throughout this portion of the talk, is that the atmosphere is really important and can save a lot of these planets. So I think it might be fun, so what I really like to do, is speculate what life on a planet like this would look like. So you get no sunlight on this side. So for example, photosynthesis couldn't happen on this side of the planet, but maybe it could happen on this side. Another weird thing is that the light that's coming in is red and not like yellowish, just like the way that our sun is. And I think a fun thing could be that maybe life would want to live on this border in between the day side and the night side, where it's like a moderate temperature. And what would be cool about living there is that it would be permanently sunset on that side. So that might be fun. You could just walk, you could have a house on each side, depending on if you wanted to sleep or not. Okay, I hope I've convinced you that tidally locked planets are in fact the best kind of planets, but I like the other planets too. We're gonna talk about the wonky floorboard planets. These are the planets that are really tilted. So Earth is slightly tilted. It has about a 23-degree tilt, which means that instead of rotating like perfectly up and down like that, it rotates kind of on its side, like this. But we think that the tilt of a planet probably is going to be pretty random. For example, Uranus, which is an ice giant in the outer solar system, is pretty much on its side. It's tilting at about 90 degrees, a little bit more than that. And the reason that tilt is important on planets is that it controls how strong the seasons are. So for example, this is Earth. It has a tiny tilt. This is summer in the northern hemisphere. So you can see that the northern hemisphere is a little bit closer to the sun. It's tilting towards the sun. Versus as the planet orbits around the star, now the northern hemisphere is pointed away from the star. So now it's winter in the northern hemisphere because it's a little bit further from the star. And so how strong this tilt is going to tell you like how different summer and winter are in terms of temperature. So like if you had a planet that's completely tilted on its side, you can see that this side of the planet is getting like blasted with sunlight. This side of the planet is getting no sunlight at all. So summer is going to be really strong in the northern hemisphere here. And then on the other side, now the northern hemisphere gets no sunlight for half the year. And the southern hemisphere is getting a bunch of sunlight. And so if you plotted the temperature in the northern hemisphere as a function of time, for Earth, we get tiny wiggles. Like we all know, I mean, we're New Englanders, we all know that it gets cold here and hot in the summer. But it's livable, right? But on a tilted planet, these temperature swings would be huge. You would have like unlivably hot and unlivably cold in the summer versus the winter. And this is a big problem because life doesn't like extremes that happen over a year instead of like 100,000 years. But like we said, the atmosphere is really important, right? The atmosphere moves hot things towards cold things. It kind of smooths out these temperature swings. And so if you had a really tilted planet, but you had a really thick atmosphere to kind of even out the temperature, maybe you could decrease how strong these cycles are, such that it would look a little bit more like Earth, and even though it would be different, you would still be able to live on a planet like this. Maybe not us, but some form of life. Okay, this one is also a pretty wacky one. This is the long commute. These are rogue planets. So when solar systems are forming, it's pretty chaotic. There's a lot of rocks flying around. And sometimes a planet is just on a really like loopy orbit, and the gravity of the star can just eject it from the solar system entirely. So these poor planets have no star. They're just wandering out on their own. This is an artist's rendition. I wish we had pictures like this of exoplanets, but we don't. And you can see this is a really lonely planet with no star. And you imagine like a planet like this, it would be so cold. Like the primary heat source on Earth is the sun. And so without a sun, how could a planet be warm? And the answer is, we don't just get heat from the sun. I mean, most of the heat does come from the sun. But remember how Earth was really molten lava hot early in its history. And over time it cooled, and it cools from the top down, which means the center of the Earth is still really hot. And a little bit of that really hot heat comes out through the rocks. And I mean, we can't feel it because it's so weak compared to the sun. But it does provide a little bit of warmth. So let's say that we put a really thick, like the thickest blanket you could ever think of atmosphere on a planet like this, which maybe could happen, who knows? Maybe that atmosphere could be strong enough and warm enough, or thick enough, to keep that tiny bit of heat on the inside from leaving. And this would warm up the planet and maybe keep it a habitable temperature. So this would be a planet that has no sun, it's dark all the time. And so what would life look like on a planet like this? And there's obviously couldn't be photosynthesis because there's no sun, but there are organisms on Earth that live in the very, very deep ocean that pretty much get no sunlight, and they're, for example, bioluminescent, so maybe they could glow and make their eyes worth having. We know that life probably formed at these vents in the ocean, the little microbes. And so I think that just because a planet doesn't have a sun or a star, there could still be some interesting life, maybe not life that we would recognize, but interesting all the same. Okay, and I'll wrap up with maybe something most clients won't like, the condo, moons. I think moons get a bad rap. I mean, we know our moon doesn't have an atmosphere. It's definitely not a good place for life. But there are other moons in our solar system, moons that we've visited with spacecrafts, that I think make really interesting case studies. So for example, my favorite moon is called Titan. Titan is a moon of Saturn, which is the planet with the pretty rings around it. And what's so cool about Titan is, number one, its atmosphere is just as thick as Earth's. And also, Titan has a water cycle, except it's not water, it's methane. So Titan has lakes of liquid methane on the surface. The methane evaporates into the atmosphere and rains as liquid methane onto the surface. So it's not a water cycle, it's a methane cycle, but it's a hydrological cycle, if you will. it doesn't, we think that if it does have water, then the water is inside of the planet, so like deep inside there might be a global ocean. I think that's still kind of up for debate. We're sending a probe called the Dragonfly over there, which maybe will tell us a little bit better. But I think that a planet like this that has liquid, that's not water, it is a hydrocarbon. I don't know, I think it could have life on it that maybe we wouldn't even recognize as life because it would be so different from ours. But hopefully Dragonfly will tell us a little bit more. Okay, let me see if I can actually get this video to play. There's another moon of Saturn's that is really exciting called Enceladus. Enceladus is really cool because this is a geyser of water that's coming out of Enceladus. So we know there's liquid water somewhere underneath the surface, and it's warm enough that it's liquid for a second. And we actually, we flew a probe through it. This is Cassini, and it's gonna fly through the geyser that's coming off of this moon, and we know that it's water. The reason why it can have liquid water is because Saturn is so big it kind of stretches the moons like a little bouncy ball, and it causes so much friction that it keeps the liquid, or the water liquid under the surface. So I'm definitely excited to hear more about Enceladus. And these are just examples of moons in our solar system. There's no reason to believe that other planets in other solar systems don't have moons too. Maybe they have moons that are really close to the star and could have a habitable temperature because it's close to its star. We haven't detected any of them yet. There's no reason to believe that they don't exist. So to wrap up this section, I hope I've convinced you that even planets very different from Earth can have liquid water somewhere. Whether it's the atmosphere that's kind of helping move heat around, or just physics maybe we don't even understand. I think that life could exist on moons, maybe in our solar system, but maybe also in other solar systems around exoplanets. And we definitely need to understand more about the atmospheres of this planet, or these planets, and I think that's kind of the crux of exoplanet science right now, is digging into these atmospheres. So to wrap up, I'm just going to leave you with this beautiful image of Earth. As much as I bragged on Earth today, it is a very special planet. We should take care of it. And this is my favorite Carl Sagan quote. The universe is a pretty big place. If it's just us, it seems like an awful waste of space. And I agree. That's from his book, Contact. And that's it. Thanks, guys.
We have more time for questions. Final reminder, if you're watching on the live stream, type any questions that you have in the chat and then we'll get them to our speaker.
Can we detect rogue planets if they don't have stars?
Yeah, great question. So I linked an article on the sheet of like a potential detection of a rogue planet. I'm not sure it's confirmed, but we have detected planets out to like 100 AU, which is 100 times further than Earth is, which is like pretty much like the sunlight you would get is so minimal that that's pretty much a rogue planet. But yeah, I think you have to use a method that's not transit, it's not crossing anything. Yeah, good question. I'm not sure. Do you know, Sophia?
Does microlensing, or do you need a star for microlensing?
I actually think it would be easier if it's really far from the closest star. I don't know if it's gravitationally bound or not, because it could be gravitationally bound, but it's just so far that it's like practically a rogue planet.
So for the first two, you talked about tidally locked planets. So I guess in that case, seasons don't really exist. It's kind
Yeah,
of just
there's
like
seasons.
an equilibrium point. And then on the other one for the tilt, seasons swing based on the tilt. And I guess somewhere in between those two is the rate of rotation of the planet around the star.
Yeah.
And so how much does that impact? Does that depend, I guess, on the thickness of the atmosphere?
How fast the planet's rotating?
For it to be acceptable to maintain like a tolerable change in climate as a function of time, or is that something that's not necessarily kind of like a parameter that's thought of too much at this point?
So do you mean how thick does the atmosphere have to be habitable, or what
Like,
the
is
rotation
there
rate?
kind of like a ratio of thickness of the atmosphere to like spread out the equilibrium temperature as a function of the rate of revolution?
I see what you're saying. Yes, so like for example, a planet that zips around its star really fast, the seasons aren't going to matter as much because it's going to be like it's going to be the time period of like a diurnal cycle or something, and so the planet won't have time to like freeze over on one side before it swings around. But I definitely think how much atmosphere you need will get bigger as a year is longer, because you're going to spend more time in winter, so you're going to need a thicker atmosphere to like keep everything insulated, definitely.
I was wondering, so you talked a lot about how like your research is surrounding like something you're interested in is like what the temperature would be like on certain planets with like different atmospheres and different conditions. And so what are like the actual temperature ranges that like you consider to be habitable, right? Because like there's so many different kinds of
Yeah.
life that like it's like we're not just caring about like if we live there, it's like if anything can live there. So I don't really
Yeah.
know like what that looks like.
Because there's just so many planets to consider and we're so new to this field, we just choose can water be liquid?
Oh, okay.
So we look at like the freezing point, the boiling point, essentially. Different people define different kinds of habitable zones, but I think the liquid water one is the most popular.
Follow-up to that would be like, I guess, I'm not sure, to what extent is like, subterranean water considered, where it's like, 'cause I know that habitable zone estimates are like liquid water on the surface, but
Yeah.
I've heard people talk a lot about like, maybe it'll freeze over on the surface, but sometime like geologically underneath there could be liquid oceans. And I wonder have people really like come up with a habitable zone for subterranean water, or what's the deal with that?
Yeah, I mean, I think that if we're gonna do a habitable zone for subsurface water, we could extend it, out to Jupiter and beyond, because we know these moons have, we know because we've been there. We know that they have water beneath the surface because of tidal friction caused by its orbit around the planet. I know that when Earth was frozen over, there was still liquid water underneath. Otherwise, everything would have died. Yeah, I think we're not in a position to be really nitpicky about what exactly we mean by habitable zone. We just have to say liquid water, and in my simulations at least, we just look at the surface temperature and we see what fraction of the planet has a surface temperature between 0 degrees Celsius and 100 degrees Celsius, and we're like, okay, well maybe not 100, that's a bit much, but 50 or something. And we were like, okay, that fraction is habitable.
And just following up on that comment, also I was listening to something about depends on the isotopes of hydrogen. It depends how much is the boiling point of the water, so it can affect. You are looking for liquid water, it can just be a little more the range
Yeah.
can be, the temperature can be different flexibility, I guess, when making these algorithms. But another question is, you talk about moons and planets, and what do you think about the Oumuamua? It was a meteorite that some people were thinking even had some I know it's hard to think, but it's a different also option for having life in this kind of not a planet but something much smaller.
Yeah, like an asteroid. Yeah. Yeah, I know there's been a lot of talk about Oumuamua. I think that some people are really optimistic that it's like an alien spaceship or something. I'm a little bit less optimistic about stuff like that, or I'm more careful, I guess. I've never modeled something like an asteroid before. I would be interested in, in order for there to be liquid water somewhere, there has to be a heat source somewhere. So whether it's from a star or from internal friction. But we do see that asteroids have water on Earth, they have ice, and we see that when they get closer to the sun and they have those contrails that follow them. So there's definitely ice and water locked in there, but whether or not it can be liquid, I'm not sure. I think it would depend on the orbit of the asteroid. But that is interesting. I like what you're thinking though. I think that we should expand this idea.
Cool. Do you have any other final questions? All right. It looks like that's it. So thank you again. And we'll have another seminar next week at the same time at 6:30 in the same room at Northwest B101. It'll also be live streamed to our YouTube, just like this week. So thank you for coming.